data, and types. We have built a foundation for thinking about programs. We understand state, instructions, sequences, branches, and repetition. We understand input, output, and failure. Now we enter a new phase. We will learn about data, what data is, how we represent it, how types help us work with data safely and correctly. This is phase 1. Data and structure. What is data? Data is information represented in a form a program can work with. Think about all the information in the world: names, numbers, dates, locations, images, sounds, text. All of this can be data if we can represent it in our program. But a program cannot work with ideas directly. It cannot understand John as a name the way humans do. It works with representations, specific patterns of bits, specific structures in memory. Data is the bridge between the real world and the program. We take information from the world, represent it as data, process it, and produce results. Understanding data means understanding how to represent the information in a way programs can manipulate. How do we represent information as data? Consider a person's age. In the real world, age is a concept, how long someone has lived. In a program, we might represent age as a number, 25. Consider a person's name. In the real world, a name is a word we use to identify someone. In the real world, a name is a word we use to identify someone. In a program, we might represent it as a sequence of characters. Alice. Consider whether someone is a student. In the real world, this is a status, either they are enrolled or not. In a program, we might represent it as a Boolean, true or false. In each case, we take something from the real world and choose a representation. The representation is not the thing itself, it is a model, an approximation that captures the aspects we care about. Choosing good representations is a fundamental skill. A poor representation makes everything harder. A good representation makes problems easy to solve. Now, what is a type? A type classifies data. It tells us what kind of data we have and what we can do with it. Consider the number 25. Is it an age, a temperature, a count? The bits in memory are the same, but the meaning is different, and the valid operations might be different. Types make this explicit. We do not just have 25. We have 25 as an integer, or 25.0 as a decimal number, or 25 as an age. Types tell us what values are valid, what operations are valid, how the data is stored. Without types, programs would be chaos. Any operation on any data, adding a name to a number, multiplying a Boolean by a date, nonsense. Types prevent nonsense. They enforce rules about what you can do with what data. Nonsense. Think of types as constraints. When you declare that a value has a certain type, you are making a promise. This value will always be of this type. It will never be something else. The program can rely on this promise. If a value is typed as an integer, the program knows it can perform arithmetic. If a value is typed as text, the program knows it can concatenate strings. These constraints might feel limiting. You cannot put a string where an integer is expected. But these constraints protect you. They prevent you from doing things that do not make sense. They catch mistakes before the program runs. They make programs more predictable and reliable. Constraints are not restrictions. Constraints are guarantees. Different types support different operations. Numbers support arithmetic, addition, subtraction, multiplication, division. You can compare them. Greater than, less than. Text supports concatenation, joining strings together. You can find the length. You can extract substrings. Booleans support logical operations and, or, not. Collections support operations like adding elements, removing elements, searching, and iterating. When you know the type of data, you know what you can do with it. The type defines the interface, the set of valid operations. Trying to perform an operation that the type does not support is an error. You cannot divide text by a number. You cannot concatenate integers. These operations do not make sense for those types. Types enforce meaningful operations. Types also determine how data is stored in memory. An integer might be stored as 32 bits. A different kind of integer might use 64 bits. Text might be stored as a sequence of bytes representing characters. This matters because storage affects what values are possible. A 32-bit integer can represent numbers up to about 2 billion. Need bigger numbers? Use a 64-bit integer or a special big number type. A single character might be stored differently in different encodings. Understanding the type helps you understand the limitations. You do not always need to think about storage, but when dealing with very large data, memory constraints, or interoperability with other systems, it matters. Types hide many storage details while still constraining what is possible. What happens when types are misused? A type error occurs when you try to use data in a way that violates its type. Assigning a string to a variable that expects an integer, type error. Calling a method that does not exist on that type error. Calling a method that does not exist on that type error. Passing the wrong number of arguments to a function, type error. Type errors can be caught at different times. Some languages check types before running, at compile time. You cannot even run the program if there are type errors. This is static typing. Other languages check types while running at runtime. The program starts but crashes when a type error is encountered. This is dynamic typing. Both approaches have trade-offs. Static typing catches errors earlier. Dynamic typing offers more flexibility. But in both cases, type errors indicate that something is wrong. Types serve another purpose: documentation. When you see that a function takes an integer and returns a string, you immediately know something about how to use it. The types tell you what to provide and what to expect. When you see a variable typed as a list of users, you know what it contains without reading all the code that created it. Types are documentation that the compiler or interpreter can check. Unlike comments, types cannot lie. If the code says a value is an integer, it is an integer. The type system enforces this. This makes code easier to understand. You can look at the types and understand the shape of the data, even without understanding all the logic. Well-chosen types communicate intent. Let us be clear about what types do and do not prevent. Types prevent certain kinds of errors, using data in ways that violate its type, passing the wrong kind of value, performing invalid operations. Types do not prevent all errors. You can still have the wrong logic. You can still have the wrong logic. You can still have bugs in your algorithm. You can still have bugs in your algorithm. You can still have bugs in your algorithm. An integer type ensures you have an integer. It does not ensure you have the right integer. Types are a safety net, not a guarantee of correctness. They catch a category of mistakes, type mistakes. Other categories require other techniques. But catching type mistakes automatically is valuable. It eliminates a whole class of bugs without requiring you to test for them explicitly. Let us summarize. Data is information represented in a form a program can work with. Types classify data. They tell us what kind of data we have. Types determine what operations are valid. Each type supports a specific set of operations. Types determine how data is stored. This affects what values are possible. Types act as constraints and guarantees. They prevent nonsense operations. Type errors occur when data is used in ways that violate its type. Types serve as documentation. They communicate what data flows through the program. Types prevent certain errors automatically. They catch type mistakes at compile time or runtime. Understanding data and types is fundamental to writing correct programs. Primitive types. In the previous video, we learned that types classify data and determine what operations are valid. Now we look at the most basic types, the primitives. These are the building blocks from which all other data is constructed. Integers, floating point numbers, booleans, characters. These are the atoms of data. Primitive types are the simplest, most fundamental types in a programming language. They are not composed of other types. They are the foundation. All complex data structures are ultimately built from primitives. Why do we have primitives? Because computers work with simple values directly. The CPU can add two integers in a single operation. It can compare two integers in a single operation. It can compare two numbers instantly. Primitive types map closely to what hardware can do efficiently. They are fast, they are simple, they are the building blocks. Different languages have slightly different primitives, but most share the core ones: numbers, booleans, and characters. Integers represent whole numbers, numbers without fractional parts. 1, 42, -7, 1,000,000. These are all integers. Integers are exact. There is no approximation. The number 42 is exactly 42, not 42, 999, or 42. The exactness is important. When counting things, users, items, iterations, you want exact values. You have 2.5 users. You have 2 or you have 3.5 users. You have 2. Integers have a range. They are stored in a fixed number of bits. Common sizes are 8, 16, 32, and 64 bits. A 32-bit integer can hold values from about -2 billion to +2 billion. Need bigger numbers? Use 64-bit integers or a special big number type. If a calculation exceeds the range, overflow occurs. The value wraps around or produces an error. Understanding integer limits matters for correctness. Floating point numbers represent decimal values, numbers with fractional parts. 3.14, -0.5, 1000.0. These are floating point values. Why floating point values? Why floating point? Because the decimal point can float to different positions. This allows representing very large and very small numbers with the same amount of storage. Floating point numbers are approximations. Unlike integers, they cannot represent all values exactly. The number 0.11 cannot be represented precisely in binary floating point. This has consequences. Adding many floating point numbers can accumulate small errors. Comparing floating point values for exact equality is dangerous. For money measurements and other precision-sensitive data, be careful with floating point. Sometimes integers or specialized decimal types are better choices. Common floating point sizes are 32 bits, single precision, and 64 bits, double precision, offers more accuracy and range. Booleans represent truth values, true or false, nothing else. Is the user logged in? True or false? Is the number positive? True or false? Did the number positive? True or false? Did the operation succeed? True or false? Booleans are the foundation of logic in programs. Every condition, every branch ultimately evaluates to a Boolean. The if statement checks a Boolean. The while loop checks a Boolean. The while loop checks a Boolean. Those simple Booleans are essential. They are how programs make decisions. Every yes/no question in a program uses Booleans. A Boolean needs only one bit, theoretically. In practice, languages often use a full byte for memory alignment reasons, but conceptually, a Boolean is the smallest meaningful piece of data. Characters represent individual symbols, a single letter, digit, or punctuation mark. A, ziz, 7, 8. H is a character. Characters are the atoms of text. A string is a sequence of characters. When you work with text, you work with characters. How are characters stored? Each character maps to a number according to an encoding. In ASCII, A is 65, A is 97 zeros 48. The encoding defines the mapping. Modern systems often use Unicode, which can represent characters from almost all writing systems. Letters, symbols, emoji, all have Unicode code points. A character type might be 8 bits, ASCII, 16 bits, many languages, or 32 bits, full Unicode. The size determines what characters can be represented. Understanding character encoding matters when working with text from different languages and systems. Each primitive type has a fixed size in bits. This size determines the range of values. For integers, 8 bits gives you -128 to +127. 16 bits gives you negative 32,778 to positive 32,767. 32 bits gives you roughly negative 2 billion to positive 2 billion, to 64 bits gives you roughly plus or minus 9 quintillion. For floating point, 32 bits gives about 7 decimal digits of precision. 64 bits gives about 15 decimal digits of precision. Why does this matter? Because choosing the wrong size can cause bugs. If you use an 8-bit integer for a count that might exceed 100 entitization, you will get overflow. If you use single precision floating point for financial calculations, you might lose precision. Choosing the right size is part of designing correct programs. Not too small or you risk overflow. Not unnecessarily large or you waste memory. Each primitive type supports specific operations. Integers support arithmetic, addition, subtraction, multiplication, division, remainder. They support comparison, equal, not equal, less than, greater than. Floating point supports the same arithmetic and comparison. But remember the precision issues. Booleans support logical operations and, or not, they support comparison for equality. Characters support comparison based on their encoding order. A is less than B because 97 is less than 98. These operations are fundamental. Everything else is built on top of them. When you add two large numbers, the CPU is ultimately performing primitive integer operations. Understanding what operations each primitive supports helps you choose the right type and avoid errors. Sometimes you need to convert between primitive types. Converting an integer to a floating point usually safe, but might lose precision for very large integers. Converting a floating point to an integer, the fractional part is lost. 3.7 becomes 3 or 4 depending on rounding rules. Converting a small integer to a larger integer, always safe. All values fit. Converting a large integer to a smaller integer, dangerous. Values might not fit, causing overflow or truncation. These conversions are called casts or coercions. Some languages require explicit casts. Others allow implicit conversion in some cases. Being explicit about conversions makes code clearer and helps avoid surprises. When you convert, you acknowledge that something might change. How do you choose which primitive to use? For whole numbers, use integers. Choose a size that fits your range with some margin. For measurements, scientific values, or calculations with fractions, use floating point. Use double precision unless memory is very constrained. For yes/no values, use booleans. Do not use integers 0/1 to represent booleans, it obscures intent. For single characters, use the character type. For text, use strings, which we will cover later. When in doubt, prefer larger sizes. Memory is usually cheap. Overflow bugs are expensive, but do not overthink it. For most cases, the default integer and floating point types are fine. Worry about size when you have a specific reason to. Let us summarize. Primitive types are the fundamental building blocks of data. Integers represent whole numbers. They are exact but have a limited range. Floating point numbers represent decimals. They have wide range but limited precision. Booleans represent true or false. They are the foundation of program logic. Characters represent single symbols. They are the atoms of text. Each primitive has a size that determines its range and precision. Primitives support specific operations, arithmetic, logic, comparison. Conversions between primitives are possible but may lose information. Choose the right primitive for your data. Consider the range and precision you need. These simple types are the foundation of all data in programs. Composite types. We have learned about primitive types, the basic building blocks, but real programs need to represent complex things. A person is not just a name or just an age. A person has a name and an age, and an address, and more. Today we learn how to combine simple types into complex structures. This is composition. Building big from small types into complex structures. This is composition. Primitive types are powerful but limited. An integer can represent an age. A string can represent a name. But what represents a person? In the real world, things have multiple attributes. A person has a name, age, address, email. A product has a name, price, quantity. An order has items, total, shipping address. To model these, we need to combine multiple values into a single unit. We need composite types. A composite type groups multiple values together. It says these values belong together. They represent one thing. This is fundamental to organizing data. Without composition, we would have disconnected primitives everywhere. With composition, we would have disconnected primitives everywhere. With composition, we have meaningful structures that mirror the real world. The most common composite type is the record, also called a struct or product type. A record bundles named fields together. Each field has a name and a type. A person record might have name of type string, age of type int, email of type string, age of type int, email of type string. All three fields belong to the same person. When you have a person, you have all three values. Records are like forms. The forms with fields exist. Each field form is an instance with specific values. Why named fields? Because names give meaning. Instead of the first string and the second string, you have name and mail. The structure documents itself. Records are everywhere. User profiles, configuration settings, API responses. Anytime you have multiple related pieces of data, records are often the answer. To use a record, you first define its structure, what fields it has and their types. Then you create instances by providing values for each field. Finally, you access fields by name. Define person his name, string, age int. Create Alice equals person with name Alice, age 30. Access Alice.name gives Alice a j. Access Alice.name gives Alice age gives 30. The record type ensures all instances have the same structure. Every person has a name and age. You cannot create a person without them. This consistency is valuable. When you receive a person, you know exactly what fields are available. No surprises. Tuples are another way to combine values. Unlike records, tuples use position rather than names. A tuple is an ordered collection of values. The first value, the second value, and so on. A pair of coordinates might be 3, 7. The first element is x, the second is y. Position determines meaning. Tuples are simpler than records. You do not need to define a new type. Just group values together, but tuples are less self-documenting. What does 3, 7 mean? Coordinates, a range, an ID and count. Without names, you must rely on context. Tuples are good for quick groupings, returning multiple values from a function, temporary pairings. When the meaning is obvious from context, records are better for important domain concepts, when you will use the structure in many places, when clarity matters. Records combine values with AND. A person has a name and an age and an email, but sometimes we need OR. A payment is made by credit card or bank transfer or cash. Not all three, exactly one. This is where choice types come in. They are also called sum types, tagged unions or variants. A choice type says a value is one of several possibilities. Each possibility may have different data. Payment method is one-off, credit card with number and expiry, bank transfer with account number, or cash with no extra data. A payment method value is exactly one of these. If it is credit card, it has card data. If it is cash, it has no extra data. Choice types model alternatives, status codes, error types, different kinds of messages. Anytime something can be this or that. When you have a choice type, you must handle each possibility. You cannot just access fields like with a record. First, you must determine which variant you have. This is pattern matching or case analysis. Check which variant, then access its data. When payment is credit card, use payment.number. When payment is credit card, use payment.number. When payment is bank transfer, use payment data number. When payment is cash, there is no data to access. The compiler can ensure you handle all cases. If you forget one, it warns you. This makes choice types safe. This exhaustive handling is a feature. It forces you to think about all possibilities. When you add a new variant, the compiler tells you everywhere that needs updating. Composite types can contain other composite types. This is nesting. An order might contain customer of type customer, another record, items as a list of order item, records, shipping address of type address, another record. Customer, order item, and address are themselves composite types with their own fields. This nesting allows modeling complex domains. A small set of primitive types becomes a rich vocabulary of structures. The key is composability. Simple types combine into records. Records combine into larger structures. Each level adds meaning while staying manageable. Good data design creates clear hierarchies. Each level is understandable on its own. The whole emerges from composing parts. When do you use each? Records, when you have multiple named attributes that belong together. The standard choice for domain objects: person, product, order. Tuples, when you need a quick grouping without defining a type. Returning coordinates. Temporary pairings, when meaning is clear from context. Choice types, when a value can be one of several alternatives. Error handling. Status codes, any is-a relationship where one type is a specific case of another. Often you combine them. A record might have a field that is a choice type. A choice type's variants might contain records. They are complementary tools. Use the one that best expresses your data structure. There is another way to build complex types: inheritance. A student is a person with additional fields. Inheritance creates an is-a relationship. A student is a person. Composition creates a has-a relationship. An enrollment has a student. Both have their place. But composition is often more flexible. With inheritance, the relationship is fixed. A student will always be a person. With composition, you can change parts independently. An enrollment can have any student. The student can be replaced. Modern practice favors composition. Build complex things by combining simpler things. This keeps each piece simple and reusable. Let us summarize. Composite types combine multiple values into a single unit. Records bundle named fields together. They are the standard way to represent domain objects. Tuples bundle values by position. They are good for quick groupings when names are unnecessary. Choice types represent alternatives. A value is one of several possibilities. Composite types can be nested. Records combine types can be nested. Records combine types can be nested. Structures build on structures. Choose the right composite for your data. Records for has these attributes. Choice types for is one of these. Composition is powerful. It turns simple building blocks into rich data models. Collections. We have learned about combining values into records. But what if you have many values of the same type, not 3 products? 30 or 3000. Today we learn about collections. Data structures that hold multiple values. Lists, sets, maps. The workhorses of data management. Programs often work with groups of things: a list of users, a set of tags, a catalog of products, a mapping of IDs to names. You cannot create a record with 1,000 fields for 1,000 products. You need a structure that holds an arbitrary number of values. Collections solve this. A collection is a container for multiple values. The number of values can vary: 0, 10, a million. Collection scale. Collections are fundamental. Almost every program uses them. Understanding collections is essential to programming. A list is an ordered sequence of elements. Elements have positions: the first element, the second element, the last element. Order matters and is preserved. Lists can contain duplicates. The same value can appear multiple times. Consider apple, banana, cherry, apple. This list has 4 elements. Apple appears twice, that is allowed. Common operations on lists: add an element, remove an element, get element at position, find if element exists, get the length. Lists are versatile: task queues, search results, message histories, anytime you have an ordered sequence of things. A set is an unordered collection of unique elements, no duplicates. Each element appears at most once. If you add an element that already exists, nothing changes. Consider apple, banana, cherry as a set. Order is not guaranteed. You cannot ask for the first element. You can only ask, is this element in the set? Why use sets? When uniqueness matters. Tags on an article. Users who have voted. Permissions a user has. You care what is present, not the order. Common operations: add element, remove element, check membership, union of 2 sets, intersection of 2 sets. Sets are efficient for membership checks. Is this user in the admin set? This is fast with sets. A map associates keys with values. It is also called a dictionary or associative array. Each key maps to exactly one value. Keys must be unique, values can repeat. Consider Alice maps to 30, Bob maps to 25, Charlie maps to 35. This map associates names with ages. Given a name, the key, you can look up the age, the value. Maps are for lookups. Given this, what is that? User ID to user data, country code to country name, word to definition. Common operations: put a key value pair, get value by key, remove by key, check if key exists. Maps are efficient for lookups. Finding a value by key is fast, regardless of how many entries exist. How do you choose which collection to use? Use a list when order matters or duplicates are allowed, a sequence of events, a queue of tasks, search results in ranked order. Use a set when you need uniqueness and do not care about order. Tags, permissions, items already processed. Use a map when you need to look up values by keys. Configuration settings, catches, any key value relationship. Often the choice is clear. Sometimes multiple collections could work. Choose the one that best matches how you will use the data. The operations you need guide the choice. Need to look up by key? Map. Need to ensure uniqueness? Set. Need ordered access? List. Collections share common operations. Size: how many elements does it contain? Empty check: is the collection empty? Contains: is this element in the collection? Iteration: go through each element one by one. These work on all collection types. The specific operations differ, but these are universal. Other operations are type-specific. Lists have indexing. Sets have union and intersection. Maps have key lookup. Learning these operations gives you a vocabulary for working with data. Most data manipulation is combining these operations. A common task is processing each element in a collection. You iterate, go through elements one by one and do something with each. For each user in users, print user.name. Iteration works with all collection types. Lists iterate in order, sets iterate in some order, but do not rely on it. Maps iterate over key value pairs. Iteration is how you transform data. Filter out unwanted elements. Transform elements to a new form. Accumulate the result. Most data processing is iteration plus operations on each element. Collections can contain collections. A list of lists, a matrix or grid. A map of lists, groups of items by category. A set of sets, groups that must be unique. Consider categories as a map where fruit maps to a list containing apple and banana, and vegetable maps to a list containing carrot and broccoli. This is a map where values are lists. Given a category, get a list of items. Nesting allows modeling complex data, but too much nesting becomes hard to understand. Often, creating name types for the inner structures helps clarity. Collections can be empty, 0 elements, an empty list, an empty set, an empty map. Empty collections are valid and important. a user with no orders, a search with no results. Handle these cases. When working with collections, always consider, what if it is empty? Does your code handle that correctly? Also consider, what if it has one element? What if it has millions? Good code works for all sizes. Let us summarize. Collections hold multiple values of the same type. Lists are ordered sequences that allow duplicates, used for sequences and queues. Sets are unordered unique collections, used when uniqueness matters. Maps associate keys with values, used for lookups. Common operations size contains iteration. Collections can be nested for complex structures. Always handle empty collections properly. Collections are fundamental. Master them and you can handle almost any data. Null and absence. Not all data is always present. Sometimes a value is missing. A user might not have a phone number. A search might find nothing. A file might not exist. How do we represent no value? This is the problem of null and absence. It is simple, but causes countless bugs. Today we understand it deeply. Consider a user profile. Name is required. Email is required, but phone number, optional. Some users have it, some do not. What do we put for the phone number when there is none? We could use an empty string, but empty string is a valid value. It is not the same as no phone number provided. We could use a special value like n/a, but that is just a string. The code might accidentally treat it as a real phone number. We need a way to say, there is no value here, not an empty value, not a placeholder, truly absent. This is what null represents. Null is a special value. That means no value or absence of value. It is not zero. Zero is a number. Null is not a number at all. It is not an empty string. An empty string is a string with no characters. Null is not a string at all. It is not false. False is a Boolean value. Null is not a Boolean. Null is the absence of any value. It represents nothing. When a variable is null, it contains no data. It does not point to anything. It is empty in a fundamental way. Null exists in most programming languages. The concept is universal, even if the name differs. Null is dangerous. If you have a value and try to use it, things work. If you have null and try to use it as if it were a value, things crash. This is the null pointer exception, the null reference error, the billion-dollar mistake as its inventor called it. You expect a user object, you call user.name, but user is null. There is no user, there is no name. The program crashes. This happens because null can appear where you expect real values. The type says user, but the value might be null. The type lies. Null turns what should be type errors into runtime crashes. The compiler says this is a user, but at runtime it is nothing. The danger comes from null being implicit. In many languages, any reference can be null. You get a user, but it might be null. You get a string, but it might be null. Every value is secretly value or null. This is implicit absence. Absence is always possible, but rarely acknowledged. Better languages make absence explicit. A type is either definitely has a value or might be absent. You must declare which. With explicit absence, the type tells the truth. If it says user, it is definitely a user. If it says user or null, you know to check. This makes null handling a conscious choice, not an afterthought. How do you work with values that might be null? First, check before using. If the value might be null, verify it is not null before accessing it. Second, provide defaults. If null, use a fallback value. Third, fail early. If null is unexpected, throw an error immediately rather than letting it propagate. First, avoid null when possible. Use empty collections instead of null collections. Use optional types that force handling. The key is being deliberate. Know where null can occur. Handle it explicitly. Many modern languages have optional types. An optional type explicitly says this might be absent. Instead of string that might secretly be null, you have optional of string. The type itself declares the possibility of absence. When you have an optional, you cannot use it directly. You must first check if a value is present. The type system enforces this. Optional types turn runtime null errors into compile time type errors. The compiler catches missing null checks. This is safer. You cannot forget to handle absence. The type reminds you. When designing data, think about which fields can be absent. Required fields, always present. Use non-nullable types. Optional fields might be absent. Use nullable or optional types. Be deliberate. If something is always required, do not allow null. This prevents accidental nulls. If something is optional, document why. When would it be absent? What should code do in that case? Consider empty values versus null. An empty list is different from no list. An empty string is different from no string. Choose the right representation. Good data modeling makes null explicit and rare. One null can lead to many null checks. If user might be null, and user.address might be null, and address.city might be null, you need checks at every step. User !address !address !city !uppercase. This is null propagation. If any step is null, the whole expression is null. You do not crash, you get null. This is convenient, but can hide problems. If something should never be null but is, the null propagates silently. You might not notice until much later. Balance convenience with clarity. Sometimes failing fast on unexpected null is better than propagating. Tony Hoare, who invented null references, called it his billion-dollar mistake. Not because null is always wrong, but because null being implicit everywhere causes enormous damage. Countless bugs, countless crashes, countless hours debugging. The lesson: absence is a special condition. It deserves explicit handling. Hiding it in every type causes more harm than good. Modern language design learns from this. Explicit optionals, non-nullable types by default, tools that help you handle absence correctly, understand null's history, respect its danger, handle it explicitly. Let us summarize. Null represents the absence of a value. It is not zero, not empty, not false. It is nothing. Null is dangerous because using null as a value crashes the program. Implicit null. A value might be null, hides the problem. Explicit null. Any value might be null, hides the problem. Explicit optional types reveal it. Handle null safely. Check before use. Provide default. Optional types make absence part of the type, forcing explicit handling. And data models distinguish required and optional fields clearly. Null propagation can be convenient but may hide problems. Respect null, it represents a real condition. Absence but requires careful handling. Immutability. Once you create a piece of data, can you change it? This question seems simple, but the answer shapes how we write code. Today we explore mutable and immutable data. Mutable means changeable. Mutable data can be modified after it is created. You create a list, you add an item. The same list now has more items. You did not create a new list, you changed the existing one. You create a record with a name field. You update the name. The same record now has a different name. The record was mutated. Mutation is in place change. The data object stays the same object, but its contents change. If you have a reference to it, you see the new contents. This is how most programming languages work by default. You create something, then you modify it as needed. Immutable means unchangeable. Immutable data cannot be modified after it is created. You create a string. You cannot change its characters. If you want a different string, you create a new one. The original remains as it was. You create an immutable list. You cannot add items to it. If you want more items, you create a new list with the additional items. The original list is untouched. Immutability is a constraint. Once data exists, it exists exactly as created, forever. No modifications, no surprises. If you want different data, you make a new copy with the changes. The old data remains unchanged. Why would we want data we cannot change? This seems like a limitation, but it brings powerful benefits. First, predictability. If data cannot change, you always know what it contains. You looked at it earlier. It had value X. It still has value X. Nothing could have changed it. With mutable data, you cannot be sure. Something else might have modified it. You must always check. You must always worry. Second, safety. If you pass immutable data to a function, you know that function cannot change it. Your data is safe. You do not need to make a defensive copy. With mutable data, any code that has a reference can modify the data. You cannot trust that your data will remain unchanged. Third, reasoning. Immutable data is easier to think about. It does not change over time. There is no before and after. There is just, it is what it is. Immutability has costs. If you want to change something, you must create a copy with the change. This means allocation, memory, time. With mutable data, you modify in place. No extra memory. With immutable data, you create a new version. More memory, at least temporarily. For small data, this cost is negligible. For large data, it can matter. Modern languages optimize this. They share unchanged parts between versions. If you change one field of a large record, the new record shares all other fields with the original. This is called structural sharing. Still, immutability is not free. There is overhead. The question is whether the benefits outweigh the costs. To understand why immutability helps, consider aliasing. Aliasing is when multiple references point to the same data. You have variable A and variable B. Both point to the same list. With mutable data, this is dangerous. You modify through A. The data changes. Someone using B sees the change. They did not ask for it. The data they relied on has silently changed. This is a common source of bugs. One part of code changes data. Another part expected it unchanged. The bug is subtle because nothing explicitly passed new data. The change happened through a shared reference. With immutable data, aliasing is safe. A and B point to the same data, but nobody can change it. A sees the data. B sees the same data. It will always be the same data. Sharing immutable data is safe. Sharing mutable data requires caution. Mutable data and concurrency do not mix well. Concurrency means multiple things happening at once. Two threads, two processes, two parts of code running simultaneously. If both access mutable data, chaos ensues. One thread writes, the other reads. What does it see? Half-written data, old data, new data? The answer depends on timing, on luck. This is a race condition. The outcome depends on who wins the race. It is unpredictable. It causes bugs that appear and disappear randomly. Immutable data eliminates this problem. Nobody can write. Everyone reads the same unchanging data. No race, no conflict. Safe concurrency. Despite its problems, mutable data has its place. Performance-critical code sometimes needs mutation. Building up a large structure piece by piece is faster with mutation than with many copies. Local mutation is often fine. If data is created, mutated, and used all within one function and never escapes, the risks are contained. Nobody else can see the mutations. Some algorithms are naturally expressed with mutation. In-place sorting. Graph algorithms that update visited nodes. Fighting against the natural expression adds complexity. The key is scope. If mutable data stays local, under your control, mutation is manageable. If mutable data is shared widely, problems multiply. Prefer immutability when data is shared. If data crosses function boundaries, immutability prevents accidental modification. If data lives in multiple places, immutability prevents synchronization problems. Prefer immutability for data that represents facts. A historical record, a snapshot of state. These should not change because they represent what was, not what is. Prefer immutability when reasoning about code. If you need to understand what a piece of code does, immutable data makes it easier. You know data input equals data output. Start with immutability. Introduce mutation only when you have a clear reason. This is safer than starting mutable and trying to add safety later. Real programs often mix both approaches. You might have an immutable data model. The records that represent your domain are immutable, but you build them up using mutable builders. Local mutation, immutable result. You might have immutable messages passed between components. Each component can have mutable internal state, immutable interpretations, mutable interpretations. The key is clear boundaries. Know what is mutable and what is not. Document it. Enforce it where possible. Do not let mutable and immutable mix unexpectedly. Let us summarize. Mutable data can be changed after creation. Immutable data cannot. Immutability provides predictability. Data you see is data you can rely on. Immutability provides safety. Nobody can change your data without your knowledge. Immutability provides safety. Nobody can change your data without your knowledge. Immutability costs extra allocations, but enables structural sharing. Mutable data is in Concurrency. Choose mutable for local performance critical operations. Choose immutable for shared data and clearer reasoning. Start immutable. Add mutation only with clear justification. Modeling with data. Programs work with data. But where does that data come from? How do we decide what data to represent and how to represent it? This is modeling. Today we learn to translate real-world concepts into data structures. Modeling is creating a representation. A map is a model of terrain. A blueprint is a model of a building. Data is a model of concepts. When you build software, you must represent things from the real world. Users, products, orders, messages. Each of these is a concept. You need data structures to capture them. Modeling is the act of deciding what data structures to capture them. Modeling is the act of deciding what data do I need, what types should that data, how do pieces of data relate to each other. A model is always a simplification. A map does not show every rock and tree. A data model does not capture every aspect of the real thing. You choose what matters for your purpose. Start by listing what you need to know about a concept. Consider a book. What matters about a book? Title, author, pages, publication year, ISBN, genre, price. But do you need all of these? If you are building a library catalog, you need title, author, ISBN. If you are building a library catalog, you need title, author, ISBN. If you are building an e-commerce site, you need price. If you are building a reading tracker, you need pages. The essential attributes depend on your purpose. A book in a library system is not the same as a book in a bookstore system. Same real-world thing, different models. Ask, what questions will the code need to answer? What operations will it perform? Those questions reveal what attributes are essential. Include only what you need. Every extra attribute is complexity. Every missing attribute limits functionality. Find the balance. Once you know the attributes, choose types for each. Title is text. Use a string. Publication year is a number. Use an integer. Price is money. Use a decimal type, not floating point. Floating point has rounding errors that cause problems with money. ISBN is a string, not a number. It might have leading zeros. It is never used for arithmetic. Each choice carries meaning. An integer says this value is numeric and can be compared and calculated. A string says this value is textual and might have any characters. Wrong types cause problems. If you store a phone number as an integer, you lose leading zeros. If you store a price as a float, you get rounding errors. If you store a price as a float, you get rounding errors. If you store a date as a string, sorting fails. Think about what the data because think about what operations you need. Choose the type that fits. Most concepts are not single values. They are groups of values. A book has title and author and pages. This is where composite types come in. You create a record or data class that groups the attributes together. A book type contains title of type string, author of type string, pages of type integer, published of type string, pages of type integer, published of type string, pages of type integer, published of type integer. My book is a type. You can have a list of books. You can pass a book to a function. The composite type gives the concept a name and a structure. It defines what a book is in your system. Concepts do not exist in isolation. They relate to each other. A book has an author, but an author might write many books. This is a relationship. An order contains products. A product belongs to a category. A user places orders. Relationships connect concepts. How do you represent relationships? One approach includes one type inside another. A book contains an author object. This works for simple cases. Another approach, use identifiers. A book has an author ID. The author exists separately. You look up the author by ID when needed. This is more flexible. The choice depends on your needs. Embedding is simpler, but creates duplication if the same author appears in many books. IDs are more flexible, but require lookups. Consider the cardinality, one-to-one, embed or reference. One-to-many, the many side, has a reference to the one. Many-to-many use a separate structure to hold the relationships. Some attributes are not just values. They are choices between alternatives. A payment method might be credit card or bank transfer or cash. A shipping status might be pending or shipped or delivered or returned. These are enumerations or choice types. A value is exactly one of a fixed set of options. Model these explicitly. Do not use strings like credit X card that can be misspelled. Do not use integers like 1, 2, 3 that are meaningless without documentation. Use an enum or sealed type that names the options. The type system then ensures you only use valid options. The compiler catches mistakes. When the options carry different data, use sealed types. Credit card payment contains card number. Bank transfer payment contains account number. Different shapes for different choices. Some attributes are always present. Some are sometimes absent. A user always has an ID, but a user might not have a phone number. Model this distinction explicitly. Required attributes use non-nullable types. Optional attributes use nullable or optional types. If an attribute is required but your model allows null, you have a bug waiting to happen. Something might set it to null. Code might If an attribute is optional but your model requires a value, you will use placeholder values like empty strings or zeros. These placeholders cause confusion. Is empty string a real value or a placeholder? Be deliberate for each attribute. Decide, is this always present or sometimes absent? Then use the appropriate type. Once you have a model, validate it against requirements. Walk through the use cases. Can this model support user registration? Can it support checkout? Can it support reporting? For each use case, check, does the model have the necessary data? Can you derive the needed information? Are the relationships correct? You might find gaps. The model lacks something needed for a use case. Edit. You might find excess. An attribute is never used. Consider removing it. You might find inconsistency. Two use cases expect different structures. Resolve the conflict. Modeling is iterative. You draft a model. You validate it. You revise it. You validate again. Repeat until the model fits the requirements. Let us model an online bookstore. We need books, authors, customers, orders, A book has id, title, price, publication year, author. We reference author by ID. An author has id then name, biography. A customer has id then name, biography. A customer has id then name, biography. Address is a composite, street, city, postal code, country. An order has id then customer id then order has id as items. Status is a choice, pending, paid, shipped, delivered, cancelled. Items is a list of order lines. An order line has book id, quantity, price at purchase time. We store price at purchase because book price might change later. This model captures the essential entities and their relationships. Each type is focused. Each attribute has a purpose. Let us summarize. Modeling is translating real-world concepts into data structures. Start by identifying essential attributes, only what your use cases need. Choose appropriate types for each attribute. Types carry meaning. Compose types to represent concepts. Use records or data classes. Represent relationships with embedding or references. Use choice types for alternatives. Distinguish required from optional attributes. Validate the model against use cases. Iterate until it fits. Good models are simple, complete, and match the domain. Data validation. Data enters your program from the outside world. Users type input. Files contain data. APIs send responses. How do you know this data is correct? Today we learn to validate data and reject what does not meet requirements. Data from outside is not trustworthy. A user might enter an email without an sign. A file might have a negative price. An API might return a date in the wrong format. If your code assumes valid data and gets invalid data, problems happen. Calculations produce wrong results. Databases store garbage. The program crashes. Invalid data is not just a problem at the point of entry. It propagates. Bad email gets stored. Bad email gets used in reports. Bad email gets sent to other systems. The corruption spreads. Validation is the practice of checking data against rules before accepting it. Data that passes is valid, data that fails is rejected. Validity depends on requirements. A valid email address has an sign and a domain. A valid age is between 0 and 150. A valid price is non-negative. A valid date is in a recognized format. These are rules. Data is valid if it satisfies all applicable rules. Data is valid if it violates any rule. Rules come from the domain. The business tells you orders must have at least one item. Prices must be in dollars, not negative. User IDs must be unique. Some rules are universal. Types must match. Required fields must be present. Some rules are specific to your application. Know your rules. Document them. Implement them. Enforce them. Where should you validate? At boundaries. A boundary is where data enters your system. User input is a boundary. File passing is a boundary. API responses are a boundary. Database queries returning data is a boundary. At the boundary, you know nothing about the data. It comes from outside. It might be anything. This is where validation belongs. Inside the boundary, you can trust the data. It has been validated. Code can work with it without rechecking. This is the shell and core pattern. The shell handles input and validation. The core assumes valid data. The core is simpler because it does not handle validation. If you validate at boundaries, you validate at once. If you validate everywhere, you duplicate validation logic and might miss spots. Different kinds of checks for different purposes. Type validation. Is the data the right type? Is it a number, not a string? Is it an object, not null? Format validation. Is the structure correct? Does the email have sign? Is the date in ISO format? Range validation. Is the value within acceptable bounds? Is age between 0 and 150? Is price non-negative? Is age between 0 and 150? Presence validation. Are required fields present? Does the user have an email? Does the order have items? Consistency validation. Do related values make sense together? Is the end date after the start date? Is quantity positive when order exists? Business validation. Does the data satisfy domain rules? Is the user authorized to place this order? Does the product exist? Layer your validation. Type and format first, then range and presence, then business rules. When data is invalid, reject it immediately. File fast means stopping as soon as you detect a problem. Do not try to continue with bad data. Do not hope the problem will not matter. If email is invalid, stop. Report the error. Do not store the invalid email and discover the problem later when sending. Failing fast has benefits. The error is close to its cause. The stack trace points to where validation happened. You know exactly what was wrong. Failing late hides the cause. You find corrupted data in the database. How did it get there? When? You do not know. Fail fast makes debugging easier. Fail fast prevents corruption spreading. When validation fails, communicate clearly. Good error messages explain what is wrong. Invalid email, missing sign is better than error. Price cannot be negative is better than bad value. Error messages should help fix the problem. If a date is in wrong format, say what format is expected. If a field is missing, name the field. For users, be helpful and non-technical. For developers and logs, be specific and include values. Collect all validation errors when possible. Returning only the first error means the user must fix and resubmit repeatedly. Returning all errors at once lets them fix everything in one attempt, but be careful with sensitive data. Do not include passwords or secrets in error messages. Some conditions must always be true, not just at entry. An invariant is a condition that must hold throughout the lifetime of data. An account balance cannot be negative. A list must always be sorted. A tree must always be sorted. Initial validation ensures invariants hold when data is created. But operations might break invariants. Withdrawing money might make balance negative. Every operation that modifies data must maintain invariance. Before completing the operation, check that invariants still hold. If an operation would violate an invariant, reject it. Do not perform an operation that would leave the system in an invalid state. Invariants turn point-in-time validation into continuous validation. Validation checks if data is acceptable. Sanitization transforms data to make it acceptable. An email is invalid because it has leading spaces. You could reject it, or you could trim the spaces and accept the cleaned version. A phone number has dashes and parentheses. You could require only digits, or you could require only digits, or you could strip non-digits and normalize the format. Sanitization is convenient for users. They do not need to follow exact formats. The system cleans their input. But sanitization can be dangerous. If you sanitize a SQL injection attempt, you might not do it correctly. You might think you fixed it, but still have a vulnerability. The safest approach, sanitize for convenience, then validate the result. Trim spaces, normalize format, then check the clean data against rules. One layer of validation might fail. Add more layers. Validate in the user interface. The form checks that email has, but a malicious user can bypass the form. Validate in the API handler. The server checks the input, but you might miss a case. Validate in the database. Constraints ensure data fits the schema. This is a last line of defense. Each layer catches different failures. UE catches honest mistakes. API catches bypassed UI. Database catches bugs in API validation. This is defense in depth. Multiple layers of protection. If one fails, another catches the problem. But do not use this as an excuse for sloppy validation. Each layer should be complete. The layers are backup, not primary. Let us summarize. Data from outside is not trustworthy. Validation checks it against rules. Validate at boundaries where data enters your system. Different types of validation, type, format, range, presence, consistency, business rules, fail fast, reject invalid data immediately before it spreads. Give clear error messages that help fix the problem. Invariants ensure ongoing validity, not just initial validity. Sanitize for convenience, then validate. Use defense in depth, multiple layers of validation. Good validation prevents bad data from corrupting your system.